Section 4.1 is about basic counting techniques. So we'll start with addition. Recall from set theory that the order of A union B is equal to the order of A plus the order of B minus the order of the intersection between A and B. So recall what this means is we're saying if we want to count the number of things in A union B, it will be equal to the number of elements in A plus the number of elements in B minus the number of elements in both A and B. So I encourage you to draw some Venn diagrams and remind yourself why this makes sense. We say sets A and B are disjoint if the overlap between A and B is nothing, or the empty set. So basically we're saying two sets are disjoint if A and B have no elements in common. In this case, if I want to count the number of things in the union, because the intersection is empty, this reduces down to saying the number of things in A union B is the number of things in A plus the number of things in B. We can generalize this using the addition principle. So suppose A and B are finite disjoint sets. Then there are the order of A plus the order of B ways to choose an element from A union B. For example, Ray owns 5 bicycles and 3 cars. He can get to work using any one of these vehicles. So how many different ways can Ray get to work? Well, bicycles and cars have no overlap. Those are two different types of vehicles. So these sets are disjoint. And Ray cannot ride a bicycle and drive a car at the same time. So there's no overlap. And Ray can choose any one of the 5 bicycles or any one of the 3 cars for a total of 8 choices for ways to get to work. So when your sets are disjoint, no overlap, you simply add the elements to get the order of the union. Multiplication. Recall from set theory that the order or the number of elements in the cross product between A and B was equal to the number of elements in A times the number of elements in B. So we have the multiplication principle. Let A and B be finite sets. There are the order of A times the order of B ways to choose 2 items in a sequence when the first item comes from A and the second item comes from B. So let's go back to Ray. He has 5 bicycles and 3 cars. He plans to ride a bicycle to and from work and then take a car to dinner. How many different ways can he do this? Well, now Ray is making a sequence. We can think of that sequence like an ordered pair, bicycle, comma, car. And any one of the 5 bicycles can be paired with any one of the 3 cars. So think about like taking bicycle 1 to work, then choosing any one of the 3 cars to go to dinner. Bicycle 2 can be paired with any one of the 3 cars, and so on. So to find the number of choices here, we simply multiply. 5 bicycles times 3 cars is 15 different options for taking a vehicle to work and then a car to dinner, or a bicycle to work and a car to dinner. Other examples. How many strings of length 3 can be formed from a 26-symbol alphabet? Well, we're trying to make strings of length 3, so I like to draw in 3 blanks that we're trying to fill in. A 26-symbol alphabet is like the English alphabet, and we can choose any one of the 26 letters to go in blank 1, any one of the 26 letters to go in blank 2, and any one of the 26 letters to go into blank 3. So 26 options times 26 options times 26 options. If we multiply those numbers together, we'll get 17,576 total choices for strings of length 3. Now think about how many different strings of length 7 can be formed from a 26 symbol alphabet if no two adjacent symbols can be the same. So we're putting a little bit of a restriction on this one. We want a string of length 7, so 7 blanks to think about. How many choices for the first blank? Well, there's no restriction on blank 1. It's an open choice, so I can put any one of the 26 letters here. But let's say I choose A to go into blank 1. I cannot choose A to go into blank 2 because no two adjacent symbols can be the same. So A's out. But I could choose any one of the other 25 letters for blank 2. So there's 25 choices for blank 2. So 26 choices for blank 1, 25 for blank 2. For blank 3, let's say I chose A and then I chose B for blank 2. I cannot choose B for blank 3, but I could choose A again because they're not adjacent. 1 and 3 are not adjacent to each other. So I still have 25 choices for blank 3, and it turns out I'll have 25 choices for each of the remaining blanks. So we can multiply 26 times 25 6 times, or we can write this using an exponent, 26 times 25 to the 6th power. If you put this into a calculator, there are actually over 6 billion choices for strings of length 7, where no two adjacent symbols are the same. When a problem breaks up into disjoint cases, you want to use multiplication to count each individual case, and then use addition to tally up the separate cases. For example, how many non-empty strings of at most 3 can be formed from a 26 symbol alphabet? Well, the strings need to be non-empty, so there has to be at least one letter for the string. So we'll start there with the smallest case, the case with length 1. There's just 26 letters to choose from. So 26 options for case 1. Then I could have strings of length 2. So I'll have 26 options for each of those 2 blanks, so 26 squared. And then a string of length 3, 3 blanks to fill in with no restrictions, so 26 choices for each blank gives me 26 to the 3rd power. And that would be all of my cases, strings of at most 3, so length 1, length 2, or length 3. I used multiplication to get each of these values, and then I want to add up each case for a total of 18,278 strings of at most length 3. Here's another example. Illinois license plates used to consist of either 3 letters followed by 3 digits, or 2 letters followed by 4 digits. How many such plates are possible? Well, again, we have disjoint cases here. 3 letters followed by 3 digits has no overlap between a license plate that has 2 letters and 4 digits. So we'll treat each case separately. Let's start with 3 letters followed by 3 digits. So we have 6 blanks to fill into, and we want to think about how many choices for each blank. Well, letters from the English alphabet have 26 options, and digits could be either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there are 10 digits, including 0, which gives us 26, 26, 26 for the first 3 blanks, 3 letters followed by 3 digits, 10 times 10 times 10. Now we need the case for 2 letters followed by 4 digits. So the first 2 blanks will have 26 options since there are 26 letters. And then the last 4 blanks will have 10 choices since there are 10 digits. So we have 26 squared times 10 to the 4th for case 2. To get the total, I just need to add those individual cases, and there are 24,336,000 options for Illinois license plates. And we'll pick up in the next video with section 4.2.